Today we're going to start a new unit on electric forces and fields. We're going to start off today and over the next several days by looking at something called static electricity. Static electricity is the study of electric charges that are at rest. The study of electric charges that aren't moving around, as opposed to current electricity, which is the type of electricity that you would have in your house or in the walls of the school that you plug in your stereo to, or you plug in the projector on the ceiling to, or whatever. The flow of electric charges. Okay, we're going to focus on static electricity, electricity at rest, charges at rest. Now, the first day or so, we're just going to be going over the basics of electricity that you learned in grade 5. I know that you learned this in grade 5 because my son Andrew's in grade 5, and he literally just had a test on the stuff that we're going to be going over today here just last week. Okay, so I'm going to put that out there, and I'm going to suggest to you that you need to remember this stuff because my son Andrew in grade 5 needed to remember this stuff last week. If grade 5ers can remember this stuff, know this stuff, then grade 12ers can remember this stuff and know this stuff. First of all, we'll start off easy here. There's two types of charge. Of course, negative, positive charge, and we have negative charge, right? I remember, as I was going through Andrew's notes here last week, they learned this. Okay, they learned that there's positive charge and negative charge, and they actually learned where positive charge and negative charge comes from. They learned that positive charge comes from having more protons than electrons. We know that protons are positively charged and electrons are negatively charged. Okay, we know that positively charged objects don't result from having just protons. We know that negatively charged objects don't result from having just electrons. There's always some protons and some electrons. In fact, they're mostly balanced. But there's often a little bit more of one than the other. If there's more protons than electrons, then we have positive charge. If we have more electrons than protons, then we have a negative charge. What about a neutral charge? If an object is neutral, which for the most part objects generally are neutral, then what does that mean? Mean we have no protons and no neutrons? Yeah, it means we have the same number of protons as electrons. They balance each other out so that the total charge ends up being equal to 0. You guys know the basic structure of the atom, right? This thing right in the middle right here is called the nucleus, yeah? Inside the nucleus are two different things. What are they? Come on, you chemistry people. Sorry? The protons and neutrons. Good. Contrary to what I said in my third year university modern physics class on my Christmas exam, I still remember this because it was the stupidest thing to say when you're a physics major and you're in your third year. Somehow, I forgot that protons and neutrons were in the nucleus. Somehow, I was thinking on that exam that electrons were in the nucleus. I don't know how I thought that. Okay? Let me tell you that if you start thinking that, it's not going to go particularly well for you, because that question that I said that on, I remember still, didn't go very well for me. It's pretty hard to justify something by suggesting that the electrons are in the nucleus when they're not in the nucleus. Protons and neutrons are in the nucleus. Protons are positively charged. Neutrons are neutral. These two things aren't balanced out. Okay, protons, there's generally more protons than neutrons in the nucleus, especially for bigger atoms. Okay, smaller atoms, it tends to be more even, but not necessarily exactly even. Don't worry about the proportion. Okay, it's not a big deal for us. Surrounding the nucleus, circling around the nucleus, are these things that we call electrons, these negatively charged objects. Protons and neutrons have essentially the same charge. They do not have essentially the same mass. Which one's heavier? Protons. Protons are way heavier, about 1,000 times heavier than an electron. Protons and neutrons aren't quite the same mass, but almost. Protons and neutrons are both way, way heavier than an electron is, but still same charge. The unit of charge, this is something that you didn't learn in grade 5. The unit of charge is the Coulomb. Okay, what do we mean by that? Well, the unit for speed is meters per second. The unit for energy is joules. The unit for momentum is kilograms meters per second. The unit for charge is the Coulomb. Now, to give you some perspective as to how big a Coulomb is, what the value of a Coulomb really means, let me give you the charge in coulombs of an electron and a proton. An electron has a charge of 1.60, or I should say negative 1.60 times 10 to the minus 19 coulombs. That means in order to get a full Coulomb of charge, you would need approximately 10 to the 19 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You need that many electrons, roughly, to give you a full Coulomb of charge. So a Coulomb is a big unit. A meter is a fairly small unit for distance. A light year is a really, really big unit for distance. A Coulomb is a really, really big unit that measures charge, but it is the base unit that we use for charge. Now, having said that, you will often see, when we see charge written down, you'll often see it written not as a C, but rather you'll often see it written as a mu C or an NC. Mu C means microcoulombs, 10 to the minus 6 coulombs. NC means nanocoulombs, 10 to the minus 9 coulombs. They're all valid units for electric charge, but we often express them this way because they're more convenient to express it that way. Having said that, you want to do a calculation, you got to always go back to this. So if you see either of these, we're going to go back, convert it to coulombs, and then do our calculation with that. Anybody tell me what the charge of a proton is? It's the same thing, except it's positive, right? So we're going to say that it's positive 1.60 times 10 to the negative 19 coulombs. You need about 10 to the positive 19 protons to make a Coulomb of charge as well. So again, that Coulomb is a really, really, really big unit of charge. I'd like you to take a look at your data sheet just for a second. These numbers are on our data sheet, but it's a little bit confusing the way that it's written. So I want to point out to you exactly how we're going to find the charge of the electron and the proton, that 1.6 times 10 to the minus 19 on our data sheet. Okay, in all honesty, over the next few weeks, you're probably just going to remember the charge of an electron. But if you don't, we want to be able to find it on our data sheet as well. If you look over on the right-hand side, you see all these particles. An alpha particle, which you've never heard of yet, but you will as time goes on this year. An electron, a proton, a neutron, and then we have these fermions, okay, positrons, neutrinos. Don't worry about those until pretty close to the end of the year. These are the ones we want to focus on right now. You can see on the right-hand side, the mass of each of them is given. Electron is 10 to the minus 31. Protons and neutrons are both 10 to the minus 27, again, about 1,000 times bigger. But the charge given for the electron, the proton, and the neutron aren't given in coulombs. It just says minus 1e or plus 1e, or, of course, for the neutron, it would be 0. What's an e? What does this minus 1e thing represent, this plus 1e? Well, an e stands for an elementary charge, the smallest possible charge that we can have. The elementary charge is listed over here on the left side of your data sheet. It says an elementary charge is 1.6 times 10 to the minus 19. So an electron is negative 1 times 1.6 times 10 to the minus 19. A proton is positive 1 times 1.6 times 10 to the minus 19. So it's there, it's on your data sheet, but you've got to know where to look. Okay, you got to look here, that it's minus 1e, and then you've got to go over here and say minus 1 times that is negative 1.6 times 10 to the minus 19. Now, an alpha particle, we haven't dealt with an alpha particle yet, and we won't for a little while. But you could easily, knowing that notation now, figure out what the charge of the alpha particle is. It says it's plus 2e. So can you tell me what the charge of the alpha particle would be? Plus 2e. What would it be in coulombs? 2 times what? No, 2 times 1.6, right? Yeah, 2 times 1.6 times 10 to the minus 19. In other words, it would be 3.2 times 10 to the minus 19. Okay, does that make sense? That notation makes sense? Not sure exactly why they do that, but in the end they do, so we have to be prepared for that. Two more terms. A conductor and an insulator. At some level, we know what a conductor is and we know what an insulator is, right? Give me an example of a conductor. It's probably easier. It's probably easier for you to give me an example of a conductor than it is for you to give me a definition of a conductor right now. Give me an example of a conductor. A metal is usually a good conductor, right? Where do you see metal conductors? Copper wire in your house, right? We use copper wire. Aluminum is also a good conductor, by the way. We used to use aluminum wiring in houses, but aluminum tends to arc really easily. Arcing means that electrons will jump from one to the other. Okay, they'll jump from one wire to the other. Well, that's not such a good thing inside your wall when electrons are arcing from one wire to another. So we don't use aluminum wire in houses anymore because it's not safe. It used to cause too many fires. We use copper wire, good conductor, but doesn't allow arcing nearly as easily as aluminum does. Okay. Give me an example of something that's not a good conductor. Wood. Yeah, good. Wood's not a good conductor. Okay. Now, everything is a conductor to some degree, but wood is not a good conductor, so therefore we say it's an insulator. All right, so we've got a couple examples of a conductor and an insulator. Can you tell me what a conductor is now? If things like copper and aluminum are conductors, what are they? What do they do? What are the purpose? Essentially, yeah. Maureen said they transmit electricity. Well, they're materials in which the electrons in the outermost regions are free to move. In other words, they allow electrons to move through them. In other words, Lorene, they transmit electricity, right? Which is exactly what you said. Why are metals particularly good conductors? Logan mentioned that that metals are generally good conductors. Why are they good conductors? Well, if you know anything from chemistry, if you've taken chemistry, you know that metals have electrons in their outermost levels that are easily movable, right? They're not stuck to the nucleus very strongly. So metals tend to be good conductors because these electrons in the outer levels tend to leave pretty easily. Whereas insulators, such as pieces of wood, as Jesse said, or plastic or glass, don't. Doesn't mean they don't have electrons that can move. Okay, electrons can, but they don't move nearly as easily. They're a lot more tightly bound to the nucleus and not nearly as free to move within the substance as they are in conductors like metals. This table that you see up on the board here now, this chart that you see up on the board, you don't need a copy. Okay, it's not anything that you need to remember per se. Just want to illustrate for you varying degrees of conductivity. In other words, varying degrees of what's a good conductor, what's a bad conductor, what's a good conductor, what's a good insulator. You can see up here that silver, copper, aluminum tend to be the best conductors. Okay, we get things like wood, glass, and rubber that tend to be the worst conductors. The relative magnitude of the conductivity is listed on the left-hand side here. So if we say, if we base it on 1, okay, so let's say 1 times 10 to the 0. Okay, 10 to the 0 is our base value right here. Then we can say that silver is 10 to the 8 times. That's 100 million times better of a conductor than something that is right around here, something like germanium. Okay, whereas something like glass is 10 to the 12 times worse of a conductor than, say, germanium. So we've got these things that are conductors that you can see vary quite a lot, from 10 to the 4, let's say, all the way up to 10 to the 8. They vary by about a factor of 10,000. But then we've got these insulators that vary in terms of how poor of a conductor they are as well. Anywhere from about 10 to the minus 9, 10 to the 15 by a factor of about 1 million. Okay? Again, don't memorize these numbers. You don't even have to know which are the worst conductors and which are the best conductors, but just know some examples of conductors and some examples of insulators. Okay, the conductors are pretty easy because you can just pretty much think of any metal and you've got a pretty good conductor. The insulators, I'll just pretty much think of any non-metal and you've got a pretty good insulator for the most part. Glass, wood, rubber, plastic, right? 3 laws that I want to talk about right here. 3 laws of electric charge. You've all heard them before. It's just going to be reviewed for you. The first one, opposite charges attract each other. In other words, positive attracts negative, and negative attracts positive. We know this. Okay, this isn't new to us. Okay, at some level, I can't remember whether you learned that in grade 5 or not, but at some level you knew that in grade 5, that opposites attract. We also know that like charges repel each other. Positive repels positive. Negative repels negative. By repel, we mean pushes away. Tries to keep them from coming together. And finally, we've got this third one. It says charged objects attract neutral objects. We want to be careful with the wording of that one. We don't just say charged attracts neutral. A proton is positive. A neutron is neutral. They do not attract each other. Positive does not attract neutral. And an electron is positive. An electron is negative. A neutron is neutral. An electron does not attract a neutron. But positive objects or negative objects, things with both protons and neutrons present in them, will attract neutral objects. Again, neutral objects, not just a neutron, but things that have both protons and protons and electrons in them, but balanced out. We'll explain tomorrow why that's the case. Tomorrow why protons don't attract neutrons, but yet positive objects will attract neutral objects. For now, you're just going to have to trust me on it, okay? Positive objects, negative objects, they both attract neutral objects. One more law that doesn't really go with the first 3, but is also important for us, it's called the law of conservation of charge. The law of conservation of energy says that energy can't be created or destroyed. The law of conservation of mass or of matter says that matter can't be created or destroyed. The law of conservation of momentum says momentum before and after is the same. In other words, momentum can't be created or destroyed. The law of conservation of charge says that charge can't be created or destroyed. It can be transferred from one thing to the other. Okay, you can walk across the carpet with your leather-soled shoes and touch somebody and shock them and transfer electrons from you to them. They gained charge, you lost charge, but the total amount of charge still remains the same. We didn't create anything, we didn't destroy anything, we just moved it from one place to another. Just the same as energy can be moved from one place to the other or transformed from one type to another. But it can't be destroyed, and it can't be created. The law of conservation of anything, the law of conservation of blank, says that blank can't be created or destroyed. Doesn't matter what that word is. Okay, what's in the blank? Okay, whether it's energy or momentum or matter or charge or whatever. Blank can't be created or destroyed, transferred or transformed, but can't be created, can't be destroyed. There's lots of implications for this, a bazillion implications for the law of conservation of charge. Today we're going to do one small implication of the law of conservation of charge. And then as the unit goes on, we'll talk about more. One example here. I'm not sure why the first sentence is italicized and bolded and underlined. I didn't notice that, but it is. It says a ball that we'll conveniently call ball number 1 has a charge of plus 3 coulombs, which, remember, that's a lot of charge. 3 coulombs is a lot of charge. It touches another ball that we're conveniently naming ball 2, that has a charge of -1 coulombs, which is also a lot of charge. The first ball then touches the third ball that has a charge of -5 coulombs, and we want to find the final charge on all three of them. Boy, this sounds confusing. Okay, one touches another, and then it touches another, and then, oh, how do we do this? Well, we're going to use the law of conservation of charge to figure out what the final charge is on all three of these objects. Conservation of charge says the total charge is going to remain the same. Now, when I touch two objects together, what they want to do is balance out. They don't always perfectly balance out. If they have equal size and equal shape, then they will balance out. If one of them is really pointy and another one is more rounded, then they're not going to balance out perfect. If one is a giant object and one is a tiny object, then the giant object is able to hold a lot more charge than the tiny object is. So they're not going to balance out perfect. Whenever we do a problem where we touch two objects together, though, we'll assume that the objects are more or less equal size, more or less equal shape, so that they do balance out. So we'll assume that they balance out, even if that's not always true. Here's how we're going to do this. We're going to make a little table. Okay, we have ball number 1, ball number 2, ball number 3. We start off with a charge here in ball number 1 of +3 coulombs. Ball number 2, charge of -1 coulomb. And ball number 3 has a charge of -5 coulombs. That's where we start. Now it says ball number 1 touches ball number 2. The total charge between ball number 1 and ball number 2, if we add those up, is +2. The total charge before we touch them is +2. The total charge after we touch them is also +2. But after we touch them, they want to balance each other out. So if it's a total of +2, but they're balanced out, then what are they going to balance out to be? +1 and +1. This one stays -5 because number 3 hasn't been touched yet. Take a quick look at this. Let's look at all three of them combined here and see if the charge has remained overall the same as it should. +3, -1, -5 gives me a total charge over here of, what is that, -3? Let's look at this one now. +1, +1, -5, total charge of -3. So while the charge is redistributed, we haven't created anything, we haven't destroyed anything. The law of conservation of charge still holds. Now the first one is going to touch the third one. +1 and -5 combined are -4. They've got to stay -4 combined. But when they balance out and evenly distribute that charge, -4 is going to be distributed among the two charges as -2 and -2. So this one's going to become -2. This one's going to become -2. What's charge number 2 going to be? It's going to stay as +1, right? Because it wasn't touched in this generation or in this stage of it. Let's just count up the total charge and just make sure that we're on the right track here. -2, -2 +1 gives me total charge of -3. So when we started all this, the charge is distributed as +3, -1, -5. We had a total charge of -3. When we finished all this stuff, the charge is completely redistributed. -2, +1, -2, but the total charge was still -3, which it has to be because we can't create anything and we can't destroy anything. We good? All right, I'm going to give you 2 multiple choice questions and we're done for the day other than playing with the static ball, okay? What I'd like you to do is please answer the next multiple choice question, which is number 32, which appears on the board right now. You don't have it in front of you right now in your notes. Don't worry about writing it down because I'll get this photocopied for you for tomorrow, this package photocopied for you for tomorrow. Just answer multiple choice number 32, please, on as multiple choice number 1 in your responder, okay? All right, guys, let's take a look at this now. Almost all of you that responded said the answer was A. One person said that they weren't sure. Hey, let's take a look at it and just to make sure that we understand why the answer is, in fact, A. Notice, first of all, that we have these units here, these microcoulombs. Okay, that's pretty typical in this unit to see microcoulombs because, as again we said, a coulomb is a really, really big unit of charge. So it's not uncommon at all to see a microcoulomb or a nanocoulomb. Now, normally we want to convert that microcoulombs to coulombs. Although when we're just adding and dividing by 2, it doesn't really matter. We can stick with microcoulombs here if we want. In the end here, we have two charges, 4.5 microcoulombs and negative 2.4 microcoulombs, charge 1 and charge 2. They touch each other. Well, the total charge, when we add these up, is going to be positive 2.1 microcoulombs. The total charge has got to be 2.1 after they touch each other as well. 4.5 minus 2.4 add up to give me 2.1. They're going to balance out to be half of 2.1, or 1.05 and 1.05. Let's add those up again, just to make sure that we're still at 2.1. 1.05, 1.05, 2.1. So the answer is, each of them are going to be 1.05 microcoulombs. The fact that they're separated at a distance of 2.5 centimeters, completely irrelevant. Okay, they could have been separated 2.5 kilometers, and the answer would have been exactly the same. After they touch each other, they're going to balance out, and the charge is going to be exactly the same, regardless of how far they're spread apart. Okay, one more multiple choice question, and then we'll wrap it up for the day here. This one's a bit trickier. See what you can do with this, and then we'll go over it as a class here. Yeah, sorry, it is a numeric response, yes. Let's take a look at this one here now. Let me give you an analogy to help you to kind of understand where we're going with this question, okay? Let's say that we have an orange that has a mass of 0.25 kilograms, okay? One orange has a mass of 0.25 kilograms. Now you've got a bag of oranges at the grocery store, and that bag of oranges has a total mass of 1 kilogram. How many oranges do you have in the bag? Easy? 4, right. How'd you get that? Okay, so you divided the total mass by the mass of 1 orange, right? Okay, 1 kilogram divided by 0.25 kilograms. The total mass divided by the mass of 1 orange. Well, if we're dealing with charge, let's not divide the total mass by the mass of 1 electron or 1 orange. Let's divide the total charge by the charge of 1 electron. My total charge here is 3.6 times 10 to the minus 17 coulombs. The charge of 1 electron is 1.6 times 10 to the minus 19 coulombs. Let's divide those two numbers and see what we end up getting. We end up getting 225. So it would be the equivalent of saying 1 kilogram total mass divided by 0.25 kilograms, the mass of 1 orange. Okay, except this time we're using numbers that are a little bit more confusing because we've got these negative exponents and we're dealing with charge that we're not used to dealing with. But in the end, it's still the same thought process that we go through. Total charge divided by the charge of 1 electron. Now, listen very carefully. In Physics 30, whenever you're asked to find a number of anything, okay, whether it's a number of electrons, a number of photons, which you haven't even heard of yet, a number of anything, take the total something and divide it by the something for 1. Whether it's the total mass divided by the mass of 1, total charge divided by the charge of 1, the total energy divided by the energy for 1, the total momentum divided by the momentum of 1, the total something divided by the something for 1. Okay? And that's always going to give you a number of something, a number of electrons, a number of photons, whatever. All right? Excellent. That's it for today.